Hi guys. These are the 3.6 notes. 3.6 is theorems about roots of polynomial equations. Okay, and the big theorem that we use is the rational root theorem. It says if p over q is in simplest form and is a rational root of the polynomial equation having integer coefficients, then p must be a factor of the constant, and q must be the factor of the leading coefficient. Right? And then we put all the factors of the constant term on top, and then all the factors of the leading coefficient on bottom. Okay, so just looking at an example of a polynomial, right? Say we have 2x to the fourth plus 3x plus 7, right? This 2 is our leading coefficient. Right, which we call q, right? And then our constant, right, we know is just a number with no variable, and that is our p, right? And to find the list of possible rational zeros, we put all the factors of p, right? So, right, it'd be the factors of 7 over the factors of 2. Right? And that's how we find the potential rational zeros. Okay, so this is called the rational root theorem. Now, in these examples, what we're going to do is we're just going to list all the possible rational solutions, so rational zeros of the function. Right, so again, it's p over q, where p is our constant. Right, so they're the factors of the constant, or the factors of leading coefficient. So let's label our p and q, where our p is the constant, right, or 8, and our q is our leading coefficient, or 4. So we're going to look for the factors of 8 over the factors of 4. Okay, so the factors are 8, right, plus or minus 1, because 1 times 8, right, or negative 1 times negative 8, plus or minus 2, right, because 2 times 4, or 2 times negative 4, right, and then plus or minus 4, and then plus or minus 8, right? So 1, 2, 4, and 8 go into 8, right? And we need both terms, so it's always going to be the plus or minus. Factors of 4, right? 1 goes into 4, 2 goes into 4, and 4 goes into 4. Okay, so, right, what we need to do to list our all possible rational solutions, right? We need to do our each term on the top over each term on the bottom, right? So 1 over 1 would be plus or minus 1, right? Then plus or minus 1 over plus or minus 2 would be plus or minus 1/2. And then plus or minus 1/4 for this over this, right? Now we start with 2, right? So plus or minus 2 over 1. Plus or minus 2 over 2 would just reduce to 1, so we don't need to write that. And then plus or minus 2 over 4 reduces to 1/2 as well. So we're done with this one. Then plus or minus 4 over 1. 4 over 2 reduces to 2, we already have. 4 over 4 reduces to 1, so we already have that. Then plus or minus 8, right? And then 8 over 2 reduces to 4, we already have that. And 8 over 4 reduces to 2, we already have that. So our possible factors are plus or minus 1, plus or minus 1/2, plus or minus 1/4, plus or minus 2, plus or minus 4, plus or minus 8. Okay. All right, so I want you to do the same thing for this. So try this on your own, right? your P is your constant term, or 45, and your Q is 7. So you're finding the factors 45 over the factors of 7. So try this. I'll pause it, and then I'll show you the solutions. So here's the solutions, right? The factors of 45 are 1, 3, 5, 9, 15, and 45. And the factors of 7 are 1 and 7. So you just need to do every combination of the P over Q. All right. Now, right, what we're going to do is we're going to use that rational root theorem to actually solve and find our possible roots, whether they're real roots or complex roots. Okay. This is where it takes a good amount of time, because what you're going to have to do is test all those possible rational solutions using synthetic division. And once you get a remainder of 0, then you know that is a root, and you can reduce the from, say, to a quadratic or something like that. Okay. So first step is to list possible factors, right? P over Q. So, right, again, we're looking for factors. P is 2 over Q, which is 3. So plus or minus 1, right? And then plus or minus 2, plus or minus 1, plus or minus 3, right? So now we're going to list all, right? So we get plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 1 over 3, and plus or minus 2 over 3. Okay, so it can be, there's 8 different possibilities. So now, this is where we have to test them. Okay, so what we're going to do in step 3 is test each possible root with synthetic division to reduce to a quadratic, right? We always want to get to a quadratic, because say we get to a quadratic, we can always use the quadratic formula. Okay. Now, so what you're going to do is test these. Okay, so we can test -1 to see if it is a root, right? So -1, and then we get 3, 4, 2, -1, and -2. Right, and see if this works. 3 times 2, -3, 1, -1, 1, -1, and then 2, 0. Yep, so this works. Okay, so -1 is a root. Okay, now we're going to test other ones to reduce. Okay, because we still have, technically this gives us, right, 3x cubed plus x squared plus x minus 2, right? So we want to try and reduce it again. I'm going to try 2/3. Oh. Right, and we'll see if this reduces to 0. So bring down the 3, and we get 3. 3 times 2/3, right, is 2. So we get 3. And then again, 3 times 2/3 is 2. So we get 3, and then 3 times 2/3 is 2. So we get 0. Yes, this works. So this is also a factor 2/3, and what we have left is 3x squared plus 3x plus 3. Okay. This is not factorable. Okay, so for step 4, right, use quadratic formula to find the rest of the roots. Okay, so obviously I picked -1 and 2/3 and they worked perfectly, but obviously if I picked 1, it wouldn't give me a remainder of 0, so I'd have to redo it. Okay, so you need to, for step 3, you need to retry until remainder equals 0. Right, so you might have to start testing all of them, right? I just was able to test the right ones and I got 0 for both of them. Um, so quadratic formula, A is 3, B is 3, C is 3, right, from this right here. So opposite of B, so x equals opposite of B plus or minus square root of B squared minus 4 times A times C over 2 times A. So we get -3 plus or minus square root. We get 9 minus 36, right, which is -27 over 6. Right. We can take out, we can take the square root of -27 is 3i square root of 3 over 6. And then we can reduce all of these by 3 and get our final solution of x equals -1 plus or minus I square root of 3 over 2, right? And we also had x equals -1 and 2/3 from up top, our real roots, okay? This is only asking for the complex, essentially, in the equation, so you only have to write the first answer, but I just wrote in the 2 real roots that we found as well. Again, though, you're gonna need to retry step 3 until you get those remainders of 0. Obviously, it could take a little extra time, right? To help you, you could kind of maybe try and graph them or look at a graph of the equation and see if you can find maybe some zeros looking at the graph and then test them using synthetic. Okay, so use some things that help you out, because obviously step 3 could take a long time if you tried the first 6 of them were wrong and then you tried -1 and 2/3 and they were right. All right, so I want you to try this one on your own, right? So try those steps. List all the factors, list the possible rational roots, right? Test using synthetic. Again, if you want to use Desmos to help you, that's fine, right? Graph them and you can maybe see where one of the roots are, right? This one's x to the 3rd, so you only need to find one root to reduce it to a quadratic, then use quadratic formula. So try this, pause this, and then I'll show you the solution. Okay, so right, your P over Q is just factors of 10 over factors of 1. So they're nice whole numbers. You just got to test them. The one that worked was x equaling 2. To reduce this to a quadratic, I didn't use the quadratic formula because it was already set up as x squared plus 5. So I could just minus the 5 and square root them. But you could obviously use the quadratic formula for that and you get the same solution. And here's some extra examples if you like to try. And then if you want to try these, I'll pause and then pause it and then I'll give you the solutions for these. But this is essentially all we're doing for this 3.6 is using the rational root theorem to figure out the possible rational and complex solutions and roots. All right, and here's the solutions for those 2 extra examples I gave you. Right, you can check your root with a graph. Like I said before, maybe go to Desmos, plug in x cubed plus 4x squared minus 9x minus 6. And you could see it's probably going to cross around -4, but you need to show me that it does have a root at -4, right? By using synthetic division and then getting it down to a quadratic.